Okay, today for this video, we're going to be simulating our first physical problem. And by simulation, I really mean a numerical calculation of what we expect the result to be. Now, the problem specifically is going to be the acceleration of a point mass inside a uniform field of force, specifically the force of gravity. So if we come over here, just have a quick slide deck. And before I get going, I really appreciate everyone that's left comments so far. I'd really ask that everyone continue to do that and provide feedback on things you think I could do better, anything I do wrong, and things that you like, and maybe I can go into more detail on future videos. Okay, so first we're going to do uniform acceleration of a point mass. The problem here is just going to be imagine picking up a stone up off the ground and then dropping it, and it gets pulled down to the ground by gravity. We're going to simplify the problem. So we have, of course, here's Isaac Newton dropping something. And the actual physical problem is, if this is a stone, it's a three-dimensional object. And it doesn't necessarily have a uniform density. So it's sort of this extended object. In addition to that, it exists in 3 dimensions. So to model it perfectly, you'd have to have a 3-dimensional calculation. But we're going to simplify it down to a 1-dimensional calculation because we really just care about its movement, towards up and down from the ground. And we're going to simplify it down and imagine the stone as a point mass. And what do I mean by point mass? Well, it's going to exist at a single position in space, so not some extended body. It takes up just an infinitesimally small piece of space, and it's going to have also some definite velocity. So we'll call position x velocity v. Now, velocity is defined as the derivative of the x with respect to time, and we might also call it x dot. Furthermore, the acceleration, which we might call x double dot, labeled it here, is the second derivative of x with respect to time. But equivalently, it's also the first derivative of the velocity with respect to time. Okay, and then some quantities we care about tracking are the particle's momentum, which is just the product of the mass and the velocity, as well as the energy, which the total energy of the system is a combination of the potential energy and the kinetic energy. And in this case, potential energy is always 1/2 mv squared, but the potential energy for the case of this problem is g, which is the acceleration due to gravity, times the height that you pick it up off the ground. Okay. So if we want to solve this analytically, and our goal is to compare against the analytical calculation, we would just set up Newton's second law here: force equals mass times acceleration. We would define the force, which in this case is mass times some constant g. We would make these two sides equal. The mass would cancel, leaving us just a constant value for the acceleration, which would be, we can set equal to x double dot, or to just a single derivative velocity. We use kind of the technique of separation and integration to get a linear increase of velocity. So this is going to be some g times time plus whatever initial velocity there is. And then we would integrate this again to get a quadratic position term with respect to time, plus a linear term times the initial velocity plus whatever initial position we have. And again, just the potential energy here, which I've called V, is equal to g times x. So again, if we come back to this picture, x is just the distance off the ground, so in 1 dimension. Okay. So when we're trying to do a numerical calculation, this is just kind of the paradigm. It's a simplified explanation of what we're trying to do. But in code, we'll give the particle some initial condition. We care about values such as position and velocity and acceleration. So these will just be, double float, double precision, real floats. that we want to update as we go. We develop some rule for updating the position for some given discrete change in time. As we go through the simulation, we want to monitor energy and momentum. In most cases, we will be conserving energy. If we are running the simulation, if we're running the calculation, and we see that energy, and we'll show that a little bit later on, but if we see the energy is not conserved, that's a cause for concern. Then we have to develop some rule for stopping the simulation. Then once we've stopped the simulation, we want to analyze the results, and when possible, we want to compare against an analytical solution. So that'd be a little bit more specific. We're just going to use an Euler integration scheme. So like I said, velocity is just the derivative of x with respect to time, and we can approximate it with some discrete form here of delta x over delta t. So those are discrete changes as opposed to derivatives. And then we just solve for delta x here. So if we know the velocity, we can just multiply out by some time. So you can think of this as kind of linearly projecting forward where you think the position will be for some change in time. And then we do the same thing for acceleration. So we have a rule now for updating the velocity, where the discrete change in velocity is just the acceleration at some given time times delta t. And these will reduce to, instead of an approximation here, so this approximation signal, it will reduce to not an approximation if you made delta t infinitely small. Okay. So as far as the steps we're going to actually implement, we're going to set the initial condition for the particle. We'll calculate the force. In this case, we don't actually need to calculate the force because it's just going to be the constant force of gravity. Then, if we know what the force is, we can calculate acceleration using Newton's second law. Then we calculate a new velocity using the first equation here. Then we can calculate the new position, again using the second equation. Reverse these. We can calculate the new velocity first, then calculate the new position. Then we can, for that given time step, we can calculate momentum and energy. And then we'll establish a boundary condition that just stops the simulation if the particle reaches the ground. So when the x position is less than or equal to 0. And then after that, we'll go ahead and compare it to an analytical solution. Okay, so let's go ahead and get started. So first, we'll go ahead and make, we'll call it uniform.f90 here. Okay. So we'll go ahead and write our program. And our end program. Implicit none. Now we'll go ahead and define our variables. But first, and I showed this in a previous video, but we're going to copy and paste in this code here, which helps us to define our kinds of real and integers. Okay, and I discussed that in a previous video why this is important. But we're going to do all of our calculations with double precision. Okay, and in a future video, I'll definitely go showing how to actually import modules, so you don't have to copy and paste this kind of code in each time. That may even be the next video, but for now, I'm just going to explicitly put everything in here. Okay, and like I said, we're going to go ahead and use double precision real values. So we define what this double precision is going to be, this dp, and then when we go ahead and define our values, we just pass it as an argument into the real kind, real type. And we're going to have several variables of this. So when we're going to have time, t. We'll have our position, x, our velocity, v, our acceleration, a. What else do we need? We also need our momentum, p, our potential energy, which I'm going to call u instead of, if I called it capital V, it would conflict with this lowercase v over here. It would say that you're trying to two variables at the same time. So I'm going to use capital U for potential energy. I'm going to use kinetic energy, Ke, for kinetic energy. And then we're going to have total energy here. And then we're going to have this double dt, which I'm going to call my delta t. Okay. So this is going to assign the type of real with a double precision kind of real for each of these variables. Okay. So now we need to go ahead and set what some of these values are going to be. So I'll go ahead and set the initial x position to 1 meter. So remember, this exclamation mark makes it a comment. So I'm just adding a comment of what my units are afterwards to keep track. And I'm going to set my initial velocity equal to 0. Okay. It's going to be meters per second. Okay. Acceleration, which is going to be constant, we'll put to 9.8. Okay. Oh yes, and again, these are going to be double precision, so we need to do our underscore dp here. Okay, and let's just go ahead and compile this really quickly. Make sure we don't have any issues. So again, to compile, we're going to call gfortran, which is our compiler, name of the file that we want to make an executable, and then we're going to call it just uniform. Okay, no problems. Now let's go and execute it. Okay, nothing. So that's good. Okay, so we have our x, v, and a, our position, velocity, and acceleration. We need to go ahead and define our delta t, which for now, I'm going to go ahead and call this, I'm going to make this a very small for this problem. I'm going to get 1 microsecond here. So 1 e to the minus 6. Okay, this is going to be units of seconds. And then these are the last of the ones that we need to define. Now we need to go ahead and calculate out our sort of derived quantities. So first we can do, and I forgot mass as well. So we need an m for mass, and we're just going to set that to 1 kilogram. Okay, so now we'll go ahead and do our derived quantity. So momentum is just going to be equal to the product of mass times velocity. Our potential energy is going to be equal to acceleration is a vector quantity, so it's pointing down. So I should have made this negative 9.8. So our potential energy is just going to be acceleration times our x position. So remember, x is how far up off the ground we are. And I'm actually going to make this an absolute value of these. That way, because a times x would give me possibly a negative number. If x is positive and acceleration is negative, then that'll give me a negative number. The absolute value is just going to take the magnitude of it. I haven't introduced this yet, but this is the notation. This is a built-in function. So absolute value of -1 would be 1. Absolute value of +1 would still be 1. That's, yeah. So we basically pass this. A times x is going to be passed into absolute value to give give the value of the potential energy. Now, kinetic energy is going to be ½ times the mass times velocity squared. So this double star gives me to the second power, while the single star gives me a product. And again, I didn't do 1/2 because 1 divided by 2 would be 2 integers. And I'll go over how integer division is done in a future video, but I just want everything to be floats right now. So we go ahead and make this a 0.5 double precision. And then finally, the total energy is just going to be equal to the potential energy plus the kinetic energy. Okay. So then we'll go ahead and print this out. And we need to have a comma in between each one. So that way we can make a comma separated value. Okay. So let's see, we have t, we have x. We have the accelerator velocity. Acceleration. Momentum, P. Then we have our potential energy. We have our kinetic energy. Then we're going to have our total energy here. Okay. Let's see. So now we'll go ahead and just test to make sure that this is right. We'll go ahead and catch if I messed up something with the printing, which is very possible. I already see 2 commas right here, which we don't need. And then we also don't need one here at the U or kinetic energy. Or right here. Okay. Let's see if this. We'll see if this works or not. You need a comma here. Okay, I was mistaken. We do need the commas. And again, I'm adding these commas in just so that way we make an actual comma-separated value. We can make a comma-separated value file. Okay, so let's see if this works. Nice. Okay, so now when I actually execute it, we're going to get a single print, which right here is not very useful on account of unless you're a person actually writing this, it's not super useful. But what we're going to do is we're going to pipe it, and I showed this in a previous video. So the output we're going to actually pipe into an output file, which I'm going to call uniform.out. And then when we go into uniform.out, we can see it's in a comma-separated format now, okay? Which I'll show reading that in later into a... I'll show reading that in to a pandas data frame in just a little while. Okay. So I'm just double checking this one more time. We accidentally added in an extra comma here that we didn't need. Okay. All right. So now we're going to go ahead and do the numerical calculation. So we'll go ahead and use a do while loop, which means that we're just going to keep looping, doing the same series of executions until some condition is met. And like I said, we're starting x at a positive value. We're letting it drop to the ground until it hits the ground. So we'll run the simulation until x is less than or equal to 0.0. Okay, and we'll undo. So now we need to go ahead and update what's going on. So first we'll update the time. which should have given. We're going to start. We need to give it an initial value for the time. So we'll set time equal to 0.0, which makes sense. Okay. I'll go and just add in comments here just for completion. So this is going to be in kilograms, meters per second. Potential energy, because we're using SI units, so specifically because we're using kilograms, meters, seconds, these things, energy is just going to be in the units of joules, which is the SI unit. That's nice and easy. Okay. So first, we'll update time. So t is going to be equal to what it was before, plus what we define as our increment of time, which is 1 to the minus 6. Then we'll update our velocity, which is just going to be equal to what velocity was before, plus the acceleration times delta t. And Fortran will follow the usual order of operations. So parentheses, exponents, multiplication, division, addition, then subtraction. And then if things are equal, then they'll move left to right. So it'll do multiplication, division from left to right. Okay. So we have an update time step here. And we have an update velocity. And notice I don't actually have to calculate force and then calculate acceleration because, again, if we remember from the PowerPoint deck, it's the acceleration is constant. So then we'll go and update our position here. So this is going to be the position it was plus the velocity times delta t. Okay. And since the acceleration is a negative number here, and the initial velocity is 0, the acceleration is negative, the difference in time is a positive number, so a negative times a positive is a negative. That'll make the velocity decrease towards a negative value, which means towards the ground. And x will decrease until it hits less than or equal to 0, at which point the looping will stop, and that will be the end of the code. Okay. So let's compile and see if it works. So I won't pipe it out yet. We'll just compile and execute it. Okay, sweet. So just double checking really quickly. Okay. Well, it ran, but we didn't print out the values, and we also didn't calculate out our other quantities. So we're going to go ahead and copy and paste these 5 lines here. So 1, 2, 3, 4, 5, 6. So I'll do this is vim, so I can hit 6, then hit YY twice, or do a yank that copies 6 of the lines. I can come down here and hit P, and that'll paste them in. And then I just need to tab them over here to get just for cleanliness. So again, we're going to do an update on the time, position, and velocity, and then we're going to recalculate out our conserved quantities that we care about, and then we'll print them to the screen. Okay. Now I'll actually pipe it into uniform.out. Let's look at uniform. Okay, and I'm only seeing one print, so something's wrong here. I did do while x is less than 0. So since I set x to 1, it should be while x is greater than or equal to 0. Okay, that's why. It was not actually executing the for loop. So it wasn't breaking. It was just, yes. Okay, very good. Now let's see what happens. There we go. Okay. See here, now it's running through the loops, printing them out to screen. We can't do much with this, so we're going to go ahead and pipe it to the output. It's going to, each time you do this, it's going to overwrite the uniform.out. So let's look at uniform.out. And here we go. Now we have our nice long list of, let's see how many time steps did we actually do. So overall, there were 451,755 loops, okay, time steps. So it's a quite resolved time step. So let's go ahead and actually look at what that looks like. So beforehand, I made a Jupyter notebook. And if people want me to, I can go over setting this up. But this is going to be written in Python. I'm just importing libraries I need. And then I have 2 functions, which are representing the analytical functions, the analytical solution to this problem. So I have for x and for velocity. So for x naught, I'm going to set it back to what it was. Here we go. So remember, position started at 1 and velocity is 0. Then I'm going to use a pandas data frame and go ahead and import the values. So let me make sure that I believe this should be the same as before. There we go. So this reads in just all of the columns. So we can see the time column is incrementing by 1 microsecond each time. Acceleration staying constant. We can go ahead and go through and plot everything. Okay. So in this case, acceleration is constant. We never actually update our acceleration, but that's because that's the nature of the problem. We can go ahead and plot our velocity here. So velocity starts at 0, and then over time becomes increasingly negative. In blue is the numerical calculation, so we just did using the Fortran code. In the red is the analytical calculation. Let's update this one. And then here we have our position. So the position takes on a quadratic curve. And again, we get our, we start at 1, and then it quadratically moves towards 0, and then we kill the simulation there. So it took about half a second for a 1 kilogram object to, well, it wouldn't matter what the mass of it was, right? But point being, in this case, it took about half a second for it to drop from 1 meter height. Okay. So then, pretty interestingly, we now have our 3 different energy curves. So total energy, and this is actually normalized, right? So it is potential energy, kinetic energy, and total energy. Each one is divided by the first value of the total energy. So that keeps, if everything is correct, the total energy should just stay constant, and we should just have some transfer of energy from potential energy into kinetic energy. And that's exactly what we see here. So when we start, the ball is at rest, the particle's at rest, so it has only potential energy and no kinetic energy, and those basically are symmetric against each other. Okay, and we'll see in a second that when we increase the time step, so which requires us to run less loops, it'll run faster. We'll see evidence that we'll get deviations away from the analytic value. So we'll explore that in just a second. Then finally, I want to introduce the concept of a phase space trajectory. So in these previous curves, we plotted our position, our velocity, and our acceleration versus time. But on this final curve, we're going to compare the momentum on the y-axis to the position. And this is called a phase space trajectory. So the particle will stop at a position, will start at a position of 1 meter with no momentum, and then it will make its way along this trajectory to the value of 0 position with the amount of with a negative momentum that it had. Okay, Now, this isn't that interesting, but we'll see in future videos that when we have more complicated systems, the phase space trajectory can tell us a lot about the system. So I just want to go ahead and introduce that at this point here. Okay, so now, as I mentioned, the trade-off we have in our simulation is what we set to be our hold on, let me pull open the code here. One of the things we have a choice over is what we set as our discrete time. Now remember, if we come over to the PowerPoint, the derivatives are only approximated by these discrete changes. So in this case, we had our delta t be 1e to the minus 6, so 1 microsecond, 1 millionth of a second. As we make it smaller and smaller, we get closer to the actual position. But when we make the delta t larger, we'll see in just a second that we get less and less accurate. And depending on your type of numerical scheme, the degree of inaccuracy will occur sooner rather than later. In this case, this Euler very basic integration is not very good. It also doesn't have a quantity that's a property called symplectic. This type of scheme is not symplectic, and all that means is it's not truly energy conserving. So we'll see in a second that when we start to make the time step larger and larger, we'll see that energy doesn't conserve in the problem, and that our error in the actual position calculation grows larger. Okay, so let's see that. So we're just going to go through and drop it 1 order of magnitude each time. So we'll come in here. Instead of 1 microsecond, we'll change it to 10 microseconds. Recompile. And I know it's a pain recompiling every time, and in future videos I'm going to show how to read an input file so we don't have to recompile. We can just change the input file. So that'll be, I'll do that in a future video. So let's go ahead and run it. So we've recompiled. We'll run it. And for the first few times that we increase the time step, we're actually not going to notice, at least visually, we're not going to notice any difference. Okay. Everything pretty much looks exactly the same. Okay, so let's go another order of magnitude. And again, the trade-off is accuracy versus time. The smaller we make the time step, the more accurate we get, but we have to do more runs, which takes more time, basically. Okay. Okay, it's still looking good. Let's decrease another order of magnitude. And by order of magnitude, I just mean by a factor of 10. So now we're going to be updating every millisecond. Okay, still looks pretty good. So now it's going to be every 10 milliseconds. Okay, we're going to show now with 10 millisecond. And we can see here that this section right here, now that we've increased the time step, we only have to do 45 loops, so it's quite a bit faster. Velocity looks fine, but now we see that the the position is starting to deviate from the actual analytical solution. And if we come down to the energy, we can see that the energy is starting to dissipate. So we're losing some of the total energy. And then there's this kind of artifact here of the boundary condition. And this is caused by, if we come back over here, because we made this delta t large, for when we're calculating the new position, we're sort of jumping kind of very far past the actual boundary. So that's what's causing the energy, the total energy, to kind of take a weird upkick. So we can ignore that. But again, we see the issue with increasing the discretization. And then we don't really see much here that's obviously different. But even this will begin to look pretty bad once we increase one more time. So let's go ahead and do that. Okay. See, we only actually did 5 loops. Acceleration is still going to look the same because we never update that. And actually, the velocity is going to be fine too because of the when we integrate just a constant value, it's this linear slope, so it doesn't actually matter. But we'll see a pretty dramatic, quite significantly dramatic difference now in the numerical and analytical solutions. We'll see a much larger dissipation in the energy, and then a rougher phase space trajectory. Okay. So as just a final run, we'll go ahead and change our initial conditions to be something kind of more interesting. So we'll drop our time step to back down to, let's say, e to the minus 5. We'll keep our x at the same position, so 1 meter up. But imagine you just tossed the ball directly up and gave it 100 meters per second. Really, really rocketed up, up vertically. Okay, so we're not going to change anything else about the simulation, just the initial condition, and we'll see what the effects are on the run. Now, because we're going to go up, so it's going to take it some time to decelerate and then fall back down, the overall simulation will definitely take longer, but I don't think too much longer. Okay, so let's see. Okay, it's not too long. So let's see what the outcome of that is. And then I'll go ahead and change these as well. For the analytical solution, I need to change the initial conditions to match. Okay. So much larger data frame now. So we did 2,041,815 loops. Accelerations, still exactly the same. But now the velocity starts at 100, and it's able to pick up a lot more velocity overall. And we see much more interesting position curve. So we start at 1 meter, we throw it upwards, it goes up, and as time increases, it gets all the way to some maximum value, which is around 500 meters high, and then falls back down to the Earth. Okay. And we look at the energy plot. Because in the previous time, we didn't start with any kinetic energy. We didn't start with any kinetic energy. But this time, we're actually going to start with a lot more kinetic energy than potential energy. And we see that here. And we see total energy is still conserved. But we get this interesting kind of a much more interesting exchange between kinetic energy and potential energy. So yes, okay. And then we'll see quite a bit more interesting phase space trajectory as well. Okay. All right, thank you very much. Let me know if you have any questions or if I screwed anything up terribly. Thank you.